Dear jury, first of all, thank you for being part of my jury and taking the effort of reading the thesis and following this presentation. So in this presentation, I will discuss different chapters of my PhD thesis. But before we start, I will give you a short introduction on project scheduling because all the chapters of this thesis are investigate algorithms and data sets for different kinds of project scheduling problems. So what is a project? A project consists of a set of activities that need to be executed. There are precedence constraints between activities, which means that some activities can only start once others are finished, and each activity has a certain duration. A project can be graphically represented by a graph, where each activity corresponds to a node, and the precedence constraints are represented by the arcs. A schedule is obtained by assigning start time to each of the activities. It will be precedence feasible if every activity starts only after all of its predecessors are finished. So here on the right, you see an example of a schedule for the project on the left. The make span of this schedule is 8, so it's the finish time of the last activity in the schedule. In each of the chapters, this basic project model will be extended with additional information. So the general outline of this thesis is that it addresses 3 different types of problems. In chapter 2, we develop a new solution algorithm for the discrete time cost trade-off problem. In chapters 3 and 4, we investigate instance complexity and the summary measures for the resource constrained project scheduling problem. And in chapters 5 and 6, we investigate data sets, also develop new summary measures and some algorithms for the resource constraint multi-project scheduling problem. So let's start with chapter 2. Here we propose a new solution algorithm for the discrete time cost trade-off problem. So first of all, what does this problem entail? It's a project that consists of multiple activities, but each activity can be executed in one of multiple modes. Every mode has a certain duration and a corresponding cost. And if a project manager would want to select a shorter mode, it will cost more. So as an example, we have the example project from before. Now each activity has 2 different modes. And a solution can be obtained by selecting one of the modes for each of the activities and then scheduling all the activities as soon as possible, which is shown here on the right. You can see one schedule in which for each of the activities, the second mode was chosen. For this solution, the total make span is 11 and the total cost is 13. Now, the problem or the challenge of the discrete time cost trade-off problem is to find the set of non-dominated alternatives. So by picking different modes, different solutions are obtained, but a lot of these solutions will be dominated by other ones. So they will be either more expensive than other modes while having the same duration or vice versa. So the challenge is to find all non-dominated alternatives, which is shown here on the right. All black dots are possible solutions for the given example, but only the blue dots are solutions that are not dominated. So for our approach, we base ourselves on the network reduction approach, which was originally introduced by Van Eynde et al. In 1992, but they use the activity on the arc format instead of the activity on the node format. Up till now, I have been discussing the project scheduling problem and the activity on the node format. So each activity is represented by a node. Luckily, it can be easily converted to activity on the arc format, where each arc corresponds to an activity by this algorithm of COMPUTATIONAL et al. So the network reduction approach was originally introduced by Van Eynde et al. In 1992. They proposed 3 types of different operators, and applying these operators in a sequence can reduce the complete graph to one single arc. Furthermore, they developed some theory to calculate what is the minimum number of node reductions, one of the 3 types, that is required to completely reduce a network to one arc. They also show that this number of node reductions cannot be lower than a certain lower bound, which was later called the complexity index. So as an example, here we have a graph. Again, let's say that the arcs are the activities. Based on this graph, we can calculate an auxiliary graph, which is called the complexity graph. It's a subgraph of this one. And based on this graph, we can obtain we can calculate the number of node reductions that are required. So by finding a node cover for this graph, which is shown here on the right, we know how many node reductions will need to be applied. So as there are 2 nodes in the node cover, we know that 2 node reductions will be required for this instance. Then this was purely looking at the network, but de Meulemeester et al. Extended this approach to work for the discrete time cost trade-off problem. So they extended the tree operators such that they also compute the trade-off curve for the activities that were reduced. So the first step of their approach is finding a reduction plan, so a sequence of reduction operators that reduces the whole graph to one single arc. And then in the second part, given the reduction plan, one can compute the trade-off curve or the all non-dominated solutions for the problem. For the second part, the CPU time depends on the number of node reductions in the plan and the number of modes per node reduction in this plan. So our approach builds further on the approach from de Meulemeester et al. By also taking into account the modular decomposition structure of the graph, and also by observing that applying node reductions can split the graph into smaller modules. So what does this mean? A module is a part of the graph that can be solved independently from the rest of the graph. Here in this example, we have the dotted part of the graph. For the discrete time cost trade-off problem, we could first solve this subproblem, and then we would have one remaining activity for that subgraph, and then we could solve the larger problem using this one remaining activity. We also show in the chapter that in the complexity graph, each module corresponds to a connected component. So it's relatively straightforward to find the modules in the graph by looking at the complexity graph. So here's an example of how a reduction tree would work. So we start from the initial graph or the initial problem. And first we will solve this branch of the tree. So a node reduction is applied and then some additional reduction operators. And once this is completely applied, we backtrack and then we go here where once again a node reduction is applied followed by some other operators. Most important part of this approach is that these 2 branches can be solved independently, which will improve the computational performance of the methods compared to the reduction plan approach. So the next problem is how to construct a good reduction tree, because there are many ways to construct one, and it has a large effect on the performance of the calculation algorithm. So we propose 4 exact methods and 1 heuristic method to construct reduction trees. We also implemented the 2 reduction plan approaches from de Meulemeester et al. To use as a benchmarking. So when looking at the results, we compared the reduction tree approaches to the DHEW, so the second approach from de Meulemeester et al. And here in the graphs, you can see the blue part is where the algorithm was more than 1 second faster than the DHE2. Orange part is where it was still faster, but not more than 1 second. And then green and red indicates that this approach was better. So first we look only at the solution time. So assuming that we already know the plan or the reduction tree, how long does it take to compute the trade-off curve? And then when looking at this, we see that all reduction tree approaches outperform the reduction plan approaches. So using this reduction tree really is valuable for the discrete time cost trade-off problem. However, it also takes some time to find the optimal tree. So if we combine, we also take into account this part, we obtain the total CPU time. And now we see that for the exact approaches, they do not outperform this approach. Luckily, the heuristic approach still outperforms it in most part of the instances, because the heuristic approach can almost instantaneously find a good reduction tree. So it doesn't, the first part of the computation time is very short. So in general, we can say by using a smart algorithm to construct a reduction tree, this approach is valuable, certainly when compared to the reduction plan approach, but we also compared it to a branch and bound algorithm that was later introduced by de Meulemeester et al. In 1998. We solved it on the same data set. We compare our heuristic approach with the branch and bound, and both got 1 hour to solve the problem. We can see that the branch and bound approach is better suited to solve the problem, as it could solve more instances to optimality, and also the time on average it took to solve it was a lot smaller. However, if we investigate it a little bit further, the reduction tree has a depth, which is the longest sequence of node reductions that should be applied. And we see that if the depth of the tree is 10 or less, actually, the reduction tree approach can also solve almost all instances. It's only when the depth of the tree starts increasing that the performance decreases. So to conclude this chapter, we show that the reduction tree outperforms the reduction plan approach. We also show that heuristic reduction tree construction can be fast and effective, but we also show that the branch and bound procedure is better suited actually for the problem, mainly when the reduction tree depth becomes larger. Future research could investigate a hybrid procedure where the branch and bound is combined with the reduction tree approach. So for the next 2 chapters, we look at the resource constraint project scheduling problem, and we will mainly look at can we understand what drives complexity of an instance and how can we describe instances with different measures. So in chapter 3, we will develop a new framework for instance complexity for the resource constraint project scheduling problem. So what is this problem? We have a set of activities, we have precedence constraints and durations, as with the basic model, but also each activity has a resource demand, which occurs every period. So the problem is to construct a schedule that respects both the precedence constraints, but also that never exceeds the resource capacity, as you can see here. So we develop a new theoretical framework to express the instance complexity. This was motivated by recent discovery of a dataset by Coelho and Van Eynde, in which they created a lot of instances from size 20 to 30 activities that cannot be solved with the current state-of-the-art solution procedures, which is a stark contrast to the J30 set, which is well known in literature, and all these instances can be solved very quickly to optimality. So our approach to instance complexity is to express it as the size of the search space, or in other words, we count the number of feasible schedules that are relevant for the problem, which is if we minimize make span, we will count the number of active schedules, because the optimal solution will always be an active schedule. We will take 3 approaches throughout this chapter. We start with only looking at the precedence constraints. In this case, we have a partial order, or which is the network of the graph, and we will try to count the number of linear extensions. A linear extension is a complete sequence of activities where all precedence constraints are respected. So the number of linear extensions, or a linear extension, actually corresponds to an activity list, and this is an upper bound on the number of active schedules, because one can convert a linear extension to an active schedule by using the serial schedule generation scheme. So to count the number of linear extensions, we look at, we develop a certain graph. The details are shown in the chapter. And then counting the linear extensions corresponds to counting the paths, the number of paths in this graph. So you see here, this path corresponds to this linear extension. So from a computational perspective, this can be done in polynomial time for a subclass of graphs, namely the series parallel digraphs. However, for general digraphs, it's exponential running time. But using the modular decomposition structure of a graph, we can obtain significant speedups. For the second approach, we also incorporate resource constraints. And now we have a graph which resource requirements for each of the activities and a certain availability. And now we will be counting maximal feasible extensions. A different way of looking at it is if we set all activity durations equal to, for instance, a duration of 1, then we will be counting the number of active schedules. This is equivalent to counting the number of maximal feasible extensions. So for this example, we have 3 possible maximal feasible extensions. For instance, 1, 2 3, 4 corresponds to this active schedule. So 1 and 2 are started at time 0, and 3 and 4 are started at time 1. Again, this can be done, counting the number of maximal feasible extensions can be done by counting the number of paths in a graph. It's a different one than the previous one. Again, the details can be found in the chapter. From computational perspective, this method is also exponential in running time, but we cannot find improvements using the special case of series parallel digraphs or with the modular decomposition structure. In the last approach, we also incorporate activity durations. Now we are counting maximal threshold extensions, which is also an upper bound on the number of active schedules, and it's a subset of the linear extensions. So it's a tighter upper bound than the number of linear extensions, but still it's an upper bound. I won't go into details because it's a bit more complex and it would lead too far. This method is also exponential in running time. Again, no improvements can be found with series parallel digraphs or with a modular decomposition, but also the CPU time is a lot larger than for the second approach because more information needs to be taken into account. So much that it even becomes intractable for some of the instances in our experiments. So to validate our framework, we will execute 2 studies. First study being how well can our framework classify between open instances and closed instances? And second, how well can it explain the CPU time for an optimal algorithm for closed instances? We will use 3 data sets from literature to analyze or to evaluate our framework. So in the first study, we compare the J30 set, which is the easy set, with the CV set, which is the hard set, on the 3 different approaches. And we see that the J30 set, the blue one, has a smaller number of linear extensions in general than the CV set. And also for the maximal feasible extensions, this is the case. So both in terms of precedence and resource constraints, J30 set is easier than the CV set. When incorporating activity durations, the same story holds, but there is a larger overlap than, for instance, for the second approach. So it complicates the insights a bit. So to conclude, it seems that approach 2 gives the clearest distinction between the 2 sets, so incorporating precedence and resource constraints. In the second study, we look at the CPU time. So we look at the RJ30 set, and we evaluate how well each of the measures can explain the CPU time for the instances. We can see that all 3 models explain quite a large part of the CPU time, but the first 2 approaches are a bit better than the third approach. We also see that below a certain threshold, all instances can be solved practically instantaneously, and only when going above this threshold, the CPU time starts to increase. So to conclude, we showed that the J30 set is easier than the CV set, both in terms of network and resource constraints. We also showed that it's not that straightforward to get insights regarding the activity durations. We also showed that our framework is capable of classifying easy versus hard instances and capable of explaining the CPU time. And we also show that it can be used to derive some classification rules for easy instances. Future research could evaluate the correlation between summary measures and this framework. We could also go further and investigate the equal duration RCPSP, which was a special case for the second approach. And also further research could be done on different drivers for the instance complexity. So in chapter 4, we will more focus on the summary measures for the RCPSP. So there are 2 types of summary measures. First of all, we have network measures, which describe the network structure of an instance. We evaluate 8 existing measures and 4 new ones. The LE stands for the linear extensions indicator, so it's based on the previous chapter. The resource measures, we have 4 from literature. We introduce 5 new ones. Again, the FE stands for the feasible extensions, so it's based on the second approach from the previous chapter. We will use 4 different data sets in the experiments. These 3 are the same as in the previous chapter, but we also created a new data set, which was a subset of the data sets from Van Eynde and Coelho in 2018. This one has the largest variety of both network and resource characteristics. So we will evaluate the resource measures based on three criteria. The first one being the consistency. So if two instances are very similar in terms of precedence constraints, then preferably a summary measure should also be very similar. The same holds for resource measures. So we will evaluate the consistency by checking how well a certain network measure can explain the number of linear extensions of an instance. For the resources, we look at the resource constraintness, which is also derived from the previous chapter using the theoretical framework. So looking at the network measures, we see that the order strength has the largest explanatory power, followed by the SP and the width indicator. So these are the best suited when trying to compare different instances. We also see that OS3 and OS4 perform quite well, but they do not outperform the OS, while they are being extensions that require more information. When looking at the resource measures, we see that the resource constraintness measure performs quite well, and also these two feasible sets indicators perform well. The others are not that good. The second criterion is the complexity. So how well can a summary measure explain the instance complexity? We did two types of experiments similar to the previous chapter, but here in the presentation, I will focus on the first one, namely how well can summary measures explain the CPU time for the optimal algorithm from Coelho and Van Eynde of 2018. So we tested this algorithm on these two data sets with a time limit of 1 hour. So here are the plots. We see that a lot of measures do not have a very clear relationship, but some do. So the linear extensions indicator was the best one, followed by the OS and the SP. The fourth best performing was the width indicator, but you see that they can explain quite a part of the CPU time. When looking at the resources, we see that there is a bell-shaped relationship between the values of the measure and the CPU times for practically all the measures, which confirms what was already known in the literature. The best performing measure is the FE indicator, followed by the resource strength and the FS21 measure. Note that these are perform a bit better than the network measures from the previous slide. We also combined network measures and resource measures, and then the best model could explain 63% of the variation by combining the linear extensions and the feasible extensions indicator. Note that this value is still a lot smaller than the 85% from the previous chapter. So clearly, by incorporating also this data set, we show that it's not as straightforward as it seemed from previous chapter to explain the CPU time purely by the network and the resource characteristics. So for the last criterion, we look at algorithm selection, or in other words, how well suited are certain summary measures to predict which algorithm will perform best for an instance. So we again used the BNB algorithm from Coelho and Van Eynde, but we executed it with 8 different configurations. Running time was 1 minute, and we used the summary measures to predict which of these 8 configurations would work best. Here are the results for the different measures. So we see that the AD and the SA indicator perform best for the resource measure, for the network measures, while the resource measures, all existing measures work well, and also this one. So interestingly, some of these well-performing measures did not perform well in explaining the instance complexity. So apparently these two criterion can differ quite a bit. So to conclude, we show that the order strength is actually better than the order strength 3 or 4. So incorporating additional information does not necessarily improve it. We also show that the linear extensions and the feasible extensions are actually very good, or let's say the best measures for explaining instance complexity. However, they are difficult to calculate. So if researchers want to use more straightforward measures, we suggest that they use order strength SP and the width for the network structure, and the resource strength, resource constraint list, and feasible sets for the resource structure. Now in the chapters 5 and 6, we will address the multi-project scheduling problem. So this is an extension of the RCPSP from the previous chapters, in which we do not have one project, but we have a portfolio of projects that need to be scheduled. The resource types are shared between the projects, and we will investigate two types of objective functions. First, we look at the average project delay, and second, we will also look at the portfolio delay, so the make span of the whole portfolio. We propose two new solution algorithms for the problem. In existing literature, most of the time, when schedule generation schemes are used, these work with one priority rule. So in each iteration of the scheme, an activity is selected and that one is scheduled based on this priority rule. However, if we have multiple projects, both the project and the activity are selected by one rule. So we call this the coupled schedule generation scheme, because these two decisions are coupled. We propose a new scheme, namely the decoupled schedule generation scheme, in which first a project is selected using a project priority rule, and then in a second step, an activity from this specific project is selected. In our experiments, we will test 15 existing rules for the coupled scheme, and we also propose 16 project rules and 16 activity rules for the decoupled scheme. We also implemented a genetic algorithm in which the solutions were represented as an activity list, but the focus of the operator, so for the crossovers and the mutations, was not only to look at the specific activities, but also look at the projects within the portfolio. So again, more focusing on the decoupled structure. We implemented 4 crossover operators and 7 mutation operators, and the algorithm could dynamically select these operators throughout the course of the algorithm. To evaluate our data to evaluate our solution algorithms, we looked at data sets from the literature, and we found 3 existing data sets. However, if we looked more into detail, we saw that 2 of the 3, first of all, do not contain a lot of instances. And if we plot them using their summary measures, we see that in general, a lot of parameter combinations are not present in the existing data sets. Also, even though this set contains a lot of instances, a large part of the possible combinations is not present. So to resolve this issue, we re-implemented a generation procedure of Browning and Yassin with the goal of generating data sets that cover a wider range of the instance space. We created 3 new data sets, and as you can see here, we could generate data sets that cover a wider range of instances or of parameter combinations. So for our experiments, we test them both on the existing sets and the new sets. When looking at the priority rule schemes, we see that for the APD, decoupled scheduling works best on both the existing sets and the new sets. When looking at the PDAL, on the new sets, still the decoupled schemes work better. And for the existing sets, the top 3 were coupled schemes, but then the remainder from the top 10 were all decoupled schemes. So we can say in general that decoupled scheduling is the way to go for multi-project scheduling. We also evaluated our genetic algorithm, but mainly we did this test to evaluate are the data sets that we propose challenging enough for more advanced algorithms. So how did we do this? We created a random initial population for the genetic algorithm, and we evaluated how long does it take for the genetic to beat the best performing priority rule from the previous experiment. As you can see, the genetic algorithm took the longest on this set, and then these 2 sets from our new sets. So it shows that at least some of these sets are challenging enough for more advanced algorithms. So to conclude, we propose new data sets that cover a wider range of the instance space. We also show that decoupled scheduling outperforms coupled scheduling in multi-project scheduling. Third, we show that using different data sets has an impact on which algorithms perform well. So it's very important to think about how will I design a certain data set. And we also show that these new data sets, at least some of them, are challenging enough for meta-heuristic approaches. Future research could develop new summary measures to describe multi-project instances. And also one could investigate further the power of decoupled scheduling in more advanced algorithms. So in the last chapter, we will focus on creating new summary measures for the RC-MPSP and use these to generate new benchmark data sets. So in the previous chapter, we identified some gaps. First of all, for the existing summary measures of multi-project scheduling, it was not always clear what is the range of feasible values. Second, we saw that there were interdependencies between values of different measures, which makes it difficult to generate data in a full factorial manner. And third, we also noted that there are some characteristics that can be present in a portfolio that cannot be described by existing measures. So to tackle these gaps, we proposed new summary measures in 3 different categories. In this presentation, I will focus on these 2 because these are the most specifically designed for multi-project scheduling. So in portfolio network characteristics, we want to be able to add precedence constraints between different projects in the same portfolio. For instance, it could be that some projects can only start when other projects are finished. So this we can model by adding precedence constraints between projects. And when doing this, we developed 2 measures to describe the structure of the portfolio network. So the first one is the multi-project parallelity, indicating how serial or parallel the portfolio is. So in one extreme, all projects can be executed in parallel. And in the other extreme, all projects can only be executed in a sequence due to precedence constraints. So, or it can be anything in between, but this is measured by this measure. Then the second measure, the multi-project float, indicates how tight the inter-project precedence constraints are given a certain parallelity of the network. Yeah, I won't explain it in detail. You can find it also in the chapter, but here is a small illustration. So here we have 3 projects, all with the same multi-project parallelity, but the more we go to the right, the more precedence constraints are added between the projects. So you see that the multi-project float decreases if you go to the right. Then when looking at the resource characteristics, in existing data sets, we often observed that either a resource type is completely shared over all projects or it is dedicated to one specific project. However, in practice, it could also be possible that some resource types are shared among a subset of the projects. So we want to be able to model everything in between these 2 extremes. And therefore, we will develop 3 new measures. First of all, we require the resource allocation matrix. So we have the binary version on the left-hand side, which indicates whether a certain project will require a certain resource type or not. On the right-hand side, you see the fractional matrix. So it can only have a non-zero value if on the left-hand side there is a 1, but it indicates, the fractional value indicates which percentage of the activities of this project require the resource type. So the first measure that we propose is the resource sharing ratio, which measures the density of this fractional matrix. So if all activities of all projects require all activity types, all resource types, then this measure will be equal to 1. If only each project or if each resource type is only required by one project, this sharing ratio will be equal to 0. Next to this, we also developed 2 new measures, the project dedication and the resource dedication, which indicates more how the matrix is structured. So I will give an example based on the resource dedication. If we have a low resource dedication, the resource types are equally distributed over all projects. So in this case, we see that 2 resource types are allocated to 2 projects and 2 types are allocated to 1. the higher the dedication becomes, the more unequally distributed these values become. So in the extreme for this example, one resource type will be global, so shared over all projects, and all the other all other resources will be completely dedicated to one specific project. We can do the same in the other direction, and this is what the project dedication indicates. So in total, we have 3 measures to describe this matrix. We propose a generation procedure, which can generate instances based on the target values for all the measures that we propose. And with this procedure, we generate 4 new data sets. The first one only incorporates the basic characteristics. So it's very similar to existing data sets from the literature. But we also propose 3 new data sets, which always include at least one of these 2 categories. So then we wanted to compare the new data sets to the data sets from the previous chapter. So here we are looking at the basic characteristics. So what are the network types of the individual projects, and also what is the general resource constraintness of the whole portfolio. And here we see that our new data sets are able to cover a wider variety of parameter combinations. So also the basic characteristics allow us to model a wider variety of instances. We also use a self-organizing map to evaluate the same concepts. This map clusters instances that are similar based on all their values for all the summary measures. So all instances in one cluster are very similar, and clusters that are next to each other are also relatively similar. So this is the distribution of the instances for chapter 6, so the new data sets. And this is the distribution for the previous chapter. And we see that our new data sets cover a wider range of combinations than the chapters from the previous sets from the previous chapter, apologies. So we also tested again the priority rules and the genetic algorithm from the previous chapter. And we observed for the priority rules that by adding these new characteristics into the data sets, that other rules become the best performers. So again, it's important to look at different data sets and different characteristics before we draw conclusions about which rules are best. Also, looking at the genetic algorithm, we saw that the instances with inter-project precedence relations, so sets 2 and 4, are the most difficult to obtain good solutions. While for the other 2 data sets, the genetic algorithm performed quite well. So to conclude, we propose a lot of new summary measures that allow to describe new portfolio characteristics. We also generated new data sets that cover a wide range of parameter combinations, but also we generated a data set that was similar to previous research. So researchers who still want to use the basic set can find one that is better than that from the previous chapter. We also observed that the new characteristics have an impact on the algorithm performance. So future research could collect real-life instances and map them to the feature space. So where in the feature space are real-life instances situated, so that algorithms can be tuned and tweaked towards these specific regions of the instance space. And second, researchers could also develop new solution strategies for the new characteristics that are present in the data sets. So this was a presentation that accompanies the PhD thesis. I hope it clarifies a lot. I'm looking forward to your questions and also to answering them. See you soon.